Okay, today we're going to talk about determinants. It's an exciting topic because it showcases all aspects of the tensor notation. On the other hand, you may realize that your tensor notation needs a little bit of work, and that's a good thing also. So we will use the subject of determinants, uses the tensor notation in a very intense way. There is a lot of manipulation of indices, and they're juggling and switching indices around and so forth. So in order to really enjoy it, you have to like tensor notation, and you have to like working with indices. I know that a lot of people don't, and that's okay too. There are alternatives to the tensor notation. And when it comes to determinants, maybe it's precisely the topic where some of the alternatives to the tensor notation also deserve some attention. But we will focus on things that tensor notation is perfect to. In particular, all topics where it's necessary to refer to the individual elements of the matrix for which we're calculating the determinant. This comes up first and foremost when we study the derivative of the determinant with respect to one of its entries, a very important topic. Some things the tensor notation is not perfect for. For example, manipulating rows and switching rows and columns of a matrix, multiplying a row by a number, and all of those important properties of the determinant. Those properties will stay largely behind the scenes of today's discussion. So instead we'll focus on the definition of the determinant, the product property of the determinants, cofactors, and most importantly, taking the derivative of the determinant with respect to one of its entries. And everything is based on this raw formula for the determinants. I'm assuming that you're familiar with it. It's not a very pretty formula, but it is raw. It's an explicit definition of what it takes to calculate a determinant. Of course, nobody calculates determinants according to this formula because it has n factorial terms, but I assume that you know what this formula means and technically how to work with it. So it includes a summation of all possible permutations where you multiply the sign of the permutation, 1 if it's an even permutation, and -1 if it's an odd permutation, by a combination of elements so that there's one element in each row and each column. So A1, A2, A3, that means we've taken a single element from each row. And then which column is determined by the permutation. So if the permutation is 2, 1, 3 in 3 dimensions, then this term is A1, 2, A2, 1, A3, 3. So that's how this formula reads. It has n factorial terms. N factorial terms. So too many for effective calculation, but tensor calculus will make this even worse. It'll make it n to the n terms, where most of the terms are 0, and only these survive. So that will be inefficient from the point of view of actual calculation, but it's not the efficiency that's our concern, but really writing something quite unappealing in the very appealing tensor form. So we're going to consider a system with an upper and a lower index. Its tensor properties, for the most part, don't matter in this discussion. You can think of it as a contravariant, covariant tensor, but it's really not important except in a couple of instances. So 2 indices. The whole discussion can be extended to objects with 2 lower indices or 2 upper indices, but the key is that there are 2 indices. These are the sorts of objects for which determinants are calculated. You can call them matrices. And we'll denote the determinant by the letter A. Okay, and our first task is to rewrite this in tensor form. So let's take a few good steps towards establishing what the tensor form is. Okay, let's consider first a system. I'll denote it by the letter S with, and we'll now restrict our attention to 3 dimensions. So we might continue to write n factorial, but for us and for this entire discussion, n is 3. Everything would have to change if n were any different number. So that's a disadvantage of the tensor notation. Something to keep in mind. Okay, and let's say that this system with 27 entries, or n cubed entries, is fully skew symmetric. Fully skew symmetric. It means that if we look at an entry corresponding to certain values I, j, and k, and switch two values. So, for instance, if we looked at entry S231, S231, excuse me, let's go with S213. Will be a little easier. Is that what we used over there? I forget. S213. It would be negative of S123, which can be written in this way: J, I, K. And also, if we switch the second two indices, the same property would be observed. I, J, K equals minus S, I, K, J. So it's easy to show that if the system has these two properties, then it also has the property that if we were to switch the first and the third indices, then the value would also become negative of each other. So a system that has these two, or maybe you can list them as three properties. In other words, the property that switching any of the two indices changes the sign is called fully skew symmetric. Fully skew symmetric. And of course that means that most of the entries are zero. Let's see why. Let's take a look at the entry S223. S223. Well, by this skew symmetric property, if we were to switch these two indices, the value would become minus of what it was. So on the one hand, it will become minus, opposite. On the other hand, it will remain the same because it will remain S223. So according to this property, S223 has the property that it's negative itself. So it must be 0. So S223 equals 0. In fact, most of the entries in this system equal 0. What entries would not equal 0? Well, we would only get a non-zero entry if these three numbers form a permutation. In other words, each number from 1 to 3 is represented in some order. So for example, S123 is of course not 0. S321 is of course not 0. In fact, it's minus the value of this entry because it's just one switch away from being 1, 2, 3. And there are 4 more because there are 6 permutations of numbers 1, 2, 3. There are 6 non-zero terms. And of course, all of them are somehow related to S123. For example, this one is minus 1, 2, 3. Minus S123. So let's see. So we'll have S123 equal to it will be S231. The way I think about it is sort of cycling the indices. It works when the number of indices is odd. So when 1 goes to the end and these two slide, that's because it's 2 switches away from being S123. You have to switch 1 and 3, giving us a minus sign, and then 1, now we have a 1 here, so 1 and 2, picking up another minus sign, so it's the same. And then cycling the indices one more time, we get 3, 1, 2. And continuing, let's also write the ones that are negative this. It's S213, clearly 1 switch away from being S123. We can cycle the indices, now these indices, giving us 1, 3, 2, 1, 3, 2. And finally, didn't forget the minus sign, as 3, 2, 1. So these are the 6 non-zero entries of a fully skew symmetric system, and they're all either S123 or S minus 123, or either S123 or minus S123. Okay, so one way of putting it is that this system has a single degree of freedom. It has 1 degree of freedom, and that's your choice of S123. Once you've chosen the value of S1, 2, 3. The remaining terms the remaining non-zero terms either equal it or is minus S1, 2, 3. And all of the rest terms that don't correspond to permutations are 0. And of course, it's nice that permutations make an appearance because that's what will allow us to connect this nice symbol to the definition of determinants. And of all these skew-symmetric systems with one degree of freedom, let's look at the one that for which S1, 2, 3, for which the entry 1, 2, 3 equals 1. So that those systems have their own notation. E, I, J, K. So E, I, J, K is a system, is a fully skew-symmetric system such that E1, 2, 3, E1, 2, 3 is 1. And similarly, let's define E, I, J, K with upper indices that has the exact same definition. So these two symbols have the same definitions. We'll use them. We'll use whichever one is convenient. And of course, we do wonder whether a system such as this is a tensor. What are its tensor properties? It's a bunch of constants, but so is the Kronecker delta ij. And this was a perfect tensor. So are these symbols a tensor? That's the question. But that's the question for a few minutes from now. In the next step, I will erase the board, and we will use this symbol for the definition to give for giving the definition of the determinant in tensor terms. All right. I erased everything but the definition, but the raw definition, and we will now capture this raw definition for n equals 3 in nearly tensor terms. So it'll go like this. A equals, we will now use the skew-symmetric system Eijk with upper indices. Well, actually, maybe with lower indices. Now we're going to use this definition for a system with one upper and one lower indices. So that it's an arbitrary choice. Let's choose one with lower indices. It's actually called a permutation system, if I forgot to give its definition. Eijk. Let me see, just so that it's easier to see that it's the same. Let's choose the one with upper indices. I was right the first time. All right, epsilon I, J, K, A1, I, A2, J, A3, K. I don't think words would really help to see why this definition matches this one for n equals 3, but let's see. So we still have a product of 3 entries, one from each row, if you want to think of the first index, upper index being first, and therefore responsible for the number of the rows. And now let's see. So let's first make sure, well, we have a summation, just like we had a summation here, except here it's given to us by the Einstein convention. So it's a sum over n to the n terms, 3 cubed terms, 27. But of course only the permutations survive, because we only get a non-zero entry out of Eijk when Ijk represents a permutation. So all but 6 factorial of these terms will vanish. And of course the value of E is either 1 or minus 1. 1 when it's an even permutation, and minus 1 when it's an odd permutation. So I don't think I mentioned it a few minutes ago, but I think it's clear. So there you go. This definition is actually an algebraic representation of this definition. So the advantages are that it's more compact, it's almost tensorial in its nature, except we have these explicit indices, which we never do in tensor notations. That's a bit of a problem that's about to be remedied. And it's nice and compact. Okay, The disadvantages is that it's still not tensorial fully because we have explicit indices, and it's n to the nth terms instead of n factorial terms. So there are lots of zeros. We had to add a lot of zeros to the sum in order to take advantage of the benefits of the tensor notation. So we'll ignore that. We'll just accept the fact that we're not going to use this formula for the actual calculation of tensors, of determinants. We will only use it to discover the key properties of determinants. Okay, so this is now our new definition of epsilon of the determinant A. Okay, let's discover some of its properties. Okay, let's discover its most important property. In fact, let's see what would happen if instead of this definition, I switched 2 and 1. Would we get A? Would we get minus A? Or would we get something completely different? Okay, so let's just erase this part and try to discover what would happen to this definition if I wrote A2 and A1. E, I, J, K, A2I, A1J, A3K. So this is a very important exercise because the elements that we'll encounter are very central to the study of determinants, and these are the sort of elements that you'll encounter in very many problems when working with determinants. Okay, so let's see. The first step, I'll take several steps, and in each step we must be very clear what we're doing and conclude whether the sign will change or remain the same. In the first step, I will take these two terms and trade places. And of course I can do that because these are numbers and numbers commute in a product. So that's a very simple step which does not change the value. So we're left with E, I, J, K, A1, J, A2, A2, I, A3K. So let's repeat. We did something very innocuous. We just switched two terms in a product. So that obviously keeps the term the same, keeps the value the same. In the next step, I will do some index renaming. I'll rename the index I into the index J, and I will rename the index J into the index I. So the two indices are trading their names, but because they're dummy indices in a summation, the result will be unchanged. So E, J, I, K, A1, I, A2, J, A3, K. And of course I'm doing all of these things so that I'll be able to compare this term to this term. So I'm trying to get it to be in this form as much as I can. I put 1 first, then I renamed I and J, and we're nearly there, except of course I and J are now switched in the permutation symbol. So we'll just switch them back. And this is where the full skew symmetry of the permutation system comes into play. So we end up with minus E, I, J, K, A1I, A2J, A3K. So the result is minus A. The result is minus A. All right, this is great from 2 points of view. Number one, we practiced the key steps in working with determinants, skew symmetries, and so forth. Number two, we discovered that switching two indices in this definition, leads to the change in the sign of the entire expression. This leads us to the following definition. Consider the combination E, I, J, K, A, R, I, A, S, J, A, T, K. Now there's lots of things going on. It's 27 different summations. It's 27 different summations, each with 27 terms in it. So the complexity of what the expressions represent in terms of the sheer number of terms is really growing. But what we've shown here by example is that this new system, which is a system in which R, S, and T are free variables, are free indices, are live indices, is fully skew-symmetric with respect to R, S, and T. It is fully skew-symmetric with respect to R, S, and T. Why? Because switching the values of R and S results in negative, which we showed it right here, negative of the original value. And similarly, we could show that switching S and T, and of course R and T, would result in changing the sign of the overall value. So this new system is fully skew-symmetric in R, S, and T. And if it's fully skew-symmetric in R, S, and T, it has a single degree of freedom, which is its value when R equals 1, S equals 2, and T equals 3. So, and any fully skew-symmetric system can be written as some constant times E R S T times E R S T. And what is this value? This value is the value that we would get if R, S, and T had values 1, 2, and 3. And when we plug in 1 for R, 2 for S, 3 for T, what we get is by definition A. So that constant is A. So here's our new key identity involving determinants. So this relationship is much better than this one from the tensor point of view. Why? Because there are no fixed values of indices, which is really contrary to the spirit of the tensor notation. So from now on, we will be working with this determinant because it's fully skew-symmetric. Excuse me. Because it is... All right. So from now on, we will be working with this relationship because it's fully tensorial in its nature. So it's much more attractive to us. So what I'm about to do is erase everything, write this expression on top of the board, and continue working with it. All right, so this relationship is much better than the original definition of the determinant because it has no fixed values of indices. So it's fully tensorial in its nature, and therefore much more attractive to someone who likes tensor calculus and the tensor notation. So what I'll do next is erase the board, write this at the top of the board, and just see how much information we can obtain from this wonderful relationship. Okay, we're picking up where we left off, which was this expression. And of course our goal is to have an explicit expression for the determinant A. So we want A equals something, which we don't quite have here. A is engaged in some combination on the right-hand side. In fact, this is 27, this equation captures 27 identities, quite intense, I would say. And our goal is to have A equals and some explicit relationship. So here comes a question I should have asked previously, which is what is E, I, J, K? E, I, J, K. What is this triple contraction? And it's best if you think about it on your own. I'll just give you the answer. There will be 3 factorial, six surviving terms. Each one of them will be 1. So this double contraction is actually 6, triple contraction. Has a simple value 6. Okay. 6. So this will actually allow us to isolate A by multiplying both sides of this identity by ERST, which of course will imply the triple contraction on both sides. And here we would have 6A, 3 factorial A. which allows us to write that A equals 1 over 3 factorial, better than writing 6 because it gives you a clue as to how this expression generalizes to a greater number of dimensions. EIJK ERST times ARI ASJ ATK. And of all the expressions that we've written involving the determinant, this one is most preferable. Why? Because it gives A explicitly, and it's fully tensorial in its nature. There are no live indices. Everything is expressed with the help of Einstein's notation. All the indices are dummy. It's a pure summation. Of course, it's a crazy number of terms. I'll mention it one more time. It's 27 squared terms. And only 36 of them are not zero. 36. So 36 out of 27 squared terms are not zero. So it's not a very effective formula for calculation, but that's not important. Our goal right now is not calculating the determinants, but discovering their properties. From that standpoint, this is the most attractive expression. Let's take a small step towards making it more compact, which is possible when we look at a system with one upper and one lower index. So the permutation symbols that occur, one comes with upper indices and the other one with lower indices. So they can be combined into a new term. And this term is called a delta system. And it's denoted by delta I, J, K, R, S, T. And it's defined as this product. E, I, J, K, E, R, S, T. So, several benefits, more than meet the eye. The most important, well, not the least important benefit is that it combines the two E's, the two permutation symbols, into something more compact. But the much more important application stems from the properties of this delta system. And in fact, it's one of the many delta systems, and we will now spend a little bit of time talking about it. So delta systems will actually not appear if we were dealing with a system with two lower indices, such as the covariant metric tensor, or two upper indices, such as the contravariant metric tensor. So for those types of objects, we would have to continue our discussion of determinants using the permutation systems. But with the ones where we have one upper and one lower index, this is actually a very convenient symbol. It has lots of important properties, and it's these properties that we will now briefly discuss. But just to summarize, this was a very important segment because we were able to come up with an explicit tensorial expression for the determinant. And now we're going to spend a few minutes talking about the delta systems. Okay, we're continuing to talk about determinants, and we've arrived at the subject of delta systems. I actually feel that it's best to learn the subject by reading the book, where you can go slowly and work out all the derivations very carefully. So I won't go through any of the derivations here, but I'll just give you the big idea. It's quite nice. You're actually familiar with two of the delta systems so far. One that we just introduced, and the Kronecker delta also belongs to the family of delta systems. So what's interesting is the delta system in the middle, which will just have a pair of indices on top and a pair of indices on the bottom. I'll give its definition in a moment, and you will see how the same definition can be used for all three delta systems. And in higher dimensions, to the delta systems with however many indices you want. So for this one, we introduced it just a few moments ago, so I will just give you one exercise to practice working with these systems. And it's this. Delta IJK RST multiplied by delta RST LMN. What is the result? And it's not a very hard question. If you imagine what the delta system represent in terms of the permutation systems, you will see that there will be an ERST here matched up with an ERST from this delta system. The two of them combined is ERST, that's 6 from a few minutes ago. And then we'll be left with two other permutation systems which will combine to give a new delta system. So the answer is 3 factorial delta I, J, K, L, M, N. Very nice. Okay. So now let me give you the definition of the general delta system. This is the full delta system. This is the Kronecker delta system. And let me give the definition for this one, and you will realize that it applies to this Kronecker system, to this Kronecker delta, and this full delta system. So a delta system can have one of three values: 0, -1, and 1. It's 1 when the top set of indices and the bottom set of indices are both permutations. They're both permutations of the same numbers. And it's 1 if the permutations are either both even or both odd. It's -1 if all of the same conditions hold, except one permutation is even and the other one is odd. And finally, it's 0 under all other circumstances. So it's 1 if this is a permutation and this is a permutation. There are permutations of identical sets of numbers, and the permutations have the same sign. It's -1 if the signs are opposite, and it's 0 in all other cases. So, of course, this definition applies to this Kronecker delta as well, except if they're both permutations, then they're necessarily permutations of the same numbers, because we only have 3 numbers. And it also characterizes this Kronecker delta, because it's a permutation of a single number. As long as it's a number, you can consider it a permutation. It's always an even permutation, because no permutation taking place. And it's 1 if the two permutations, well, all right. So if the two numbers are the same, it's 1 because they're permutations of the same numbers, and of course they're both necessarily even, and 0 otherwise. So this system never gets to be -1, because if it's a permutation, by definition, it will be permutation that's even, both permutations. Okay, so that's the common definition. That's the common definition. So I think this one requires a couple of examples. So, for example, delta 1, 2, 1, 3. They're both permutations, but they're not permutations of the same numbers. So this is 0. Delta 2, 2, 2, 2. They're identical sets of numbers, but this is not a permutation. So this is 0 as well. Delta 1, 2, 1, 2. Now we're in the case where it's not 0. They're identical. They're permutations of identical numbers. They're both even. So it's 1. And similarly, delta 2, 1, 2, 1 is 1 because they're both permutations of the same sets of numbers and they're both odd. And finally, to give you one that's -1, delta 1, 2, 2, 1 is -1. All right. So that's a few examples to illustrate the definition of this. So on the next board, I will write the most important properties of the delta systems. Number 1 is they turn out to all be related by contraction. So for example, if I were to take a full Kronecker system, I, J, K, R, S, and contract it on the last index, then what I will end up with is delta Ij, delta Rs. So one contraction leads to another delta system of a lower order. And if I next go ahead and contract this one, delta ij rj, what I will end up with is twice delta IR. So the first time, when you start with a full system, the first time you do a contraction, you get a coefficient of 1. The second time you do it, you get a coefficient of 2. And the third time you do it, which is of course contracting the Kronecker delta on I, you get a factor of 3 times 1. So you get not a factor of 3, you get 3. So this pattern, of course, generalizes to higher dimensions. In n dimensions, you would have n indices on top, and on the bottom you contract one of them, you get a delta system of a lower order. You do 2 more, you'll get another coefficient of 2 as the delta system of a lower order, and so forth until you come to the last one, where the contraction will result in the number n. And this is an alternative view of actually this formula. You can see where 3 factorial comes from when you contract 3 times. You contract once, you get a factor of 1. You contract the second time, you get a factor of 2. You contract the third time, you get a factor of 3. That's 3 factorial. If you kept going, you would end up with n factorial. So that's how these formulas generalize to 3 dimensions. Okay, so that's number 1. They're related by contraction. Number 2 is that, in fact, all of the Kronecker, delta systems can be expressed in terms of the Kronecker delta. So I'll start with this one, I'll start with this one, Kronecker delta of the second order, and then I'll show you the expression for this one. So we'll go in that order. So here is an expression, an identity, that is used remarkably frequently. It is used all the time, especially when you deal with curls and cross products, and especially when you deal with curl of curl or curl of the cross product or cross product of curls and so forth. So when you combine those two objects, those two operations, that's when this system appears all the time. And it can be expressed in terms of Kronecker deltas in the following way. Delta I R JS minus delta I'll write it this way. You switch S and R in the bottom, I, J, S, R. So delta IS, delta JR. It's very important to think this relationship through and realize that it's true and that it holds in all dimensions. And it's very important for 2 reasons. Well, number 1 is obvious when both are obvious. So let me just state what they are. Number 1 is whenever you encounter this symbol in your calculations, you can switch to this combination. And of course, all the delta systems and contractions play a very important role. They rename indices and disappear. So very effective for calculation. That's number 1. Number 2, it shows that this system is a tensor because it can be expressed as a tensor combination of tensors. That means from the tensorial point of view, this symbol is in fact a tensor. It is a tensor of 2 contravariant orders and 2 covariant orders. Something that's not at all easy to see from a different point of view or to prove directly. But it's this expansion, if you will, that shows that this delta system is a tensor. Okay. Now, notice, and there's no particular significance for the determinant appearing here. It's just a very good mnemonic device for remembering this formula. You can organize the Kronecker deltas in a 2x2 matrix. Like this. I, J, R, S, S, R. Let's see. No. Delta I, R, delta J. Nope, that's not working. So much for the mnemonic property. The following way. Well, let's gonna let it dry. All right. Delta, 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 delta. I, J, R, S, R, excuse me, R, S. So the top index, you can think of it as being responsible for the row that it's in. So in the first row, they're both I, in the second row, they're both J, and the second index is responsible for the column they're in. So the first column corresponds to R, and the second row corresponds to S. And of course, we have delta IR, delta JS, minus delta IS, delta JR. So this is just a convenient way, or maybe not so convenient, of remembering this expression. I don't think it's so convenient. But the convenient way comes from, the convenience of this approach becomes apparent when we try to express the full delta system in terms of individual Kronecker deltas. And I will do it here. It's also not so useful for everyday use, but it just shows that it's possible to express the full Kronecker system in terms of the full delta system in terms of the individual Kronecker symbols. So I will once again fill this 3×3 determinant with Kronecker delta systems. And all of these get an I, all of these get a J, all of these get a K, and all of these get an R, all of these get an S, and all of these get a T. Okay, so the importance of this formula is that it shows that indeed, once you wrote out the 6 terms that this determinant represents, that this delta system can be represented in terms of Kronecker deltas, therefore proving that the full delta system is a tensor of order 6 with 3 contravariant orders and 3 covariant orders. And it's also in this form that this relationship is easiest to prove. So it's this form that helps you argue that this symbol and these 6 terms in a sum are actually equal. Okay, so that's the crux of the delta systems. I will next erase the board and prove to you the all-important product multiplication property of determinants. That the determinant of a product of 2 matrices is the product of their determinants. Okay, let's demonstrate the product property of determinants. That is, if you have 2 matrices, A and B, and their product is AB, then the determinant of AB, let's write it in the matrix notation here, the determinant of AB equals the determinant of A times the determinant of B. I use this example as one of the motivations for tensor calculus, maybe for the tensor notation. I don't know of any other elegant way to prove this directly. Linear algebra books contain very elegant proofs that involve elementary matrices of this property. And whenever there's a direct proof, I actually find that it's difficult to get through and it's not at all intuitively clear. But the tensor notation offers a very short, concise, and elegant proof of this notation. So let's see what we have. Suppose we have, so for our matrices, we'll consider systems with 1 upper and 1 lower index. This argument can be very easily extended to objects with 2 lower indices or 2 upper indices, and of course linear algebra doesn't care about the placement of indices, and this is really a linear algebra discussion in tensor notation. So for convenience, we'll just consider both of these as having one upper, one lower indices. So what we have is this. CIK, that's the product. It's the matrix product, quote unquote, of AIJ and BJK. This is the tensor way of saying that C equals AB. Now let's write down the determinant of C, denoted by the capital letter C, and see if we can relate it to the determinant of A and the determinant of B. And I'm actually very curious to see whether the whole proof will fit in one line within this board. So maybe I'll try to write a little bit more compactly than I otherwise would. So it's 1 over 3 factorial times delta. All right, so we have to think the letters through. We're going to go here with I, J, K, R, S, T of C, R, C, R, I, C, S, J, C, T, K. Very good. This is the definition of the determinant, capital C. Let us now plug in the fact that C is the matrix product of A and B. So we have 1 over 3 factorial, delta I, J, K, R, S, T. Let's think about what CRI is. You need new letters, L, M, and N. So it's A, R, L, B, L, I, A, S, M, B, M, J, A, S, N, B, N, K. Okay, very good. Now we just need to combine, let's see. To combine this term with this, and this. And I just realized there's one relationship that I skipped, but I will justify it just a moment later here. A good educator would have done it in the opposite order. But when we look at these 4 terms, give me just 1 second. Their combination will be A, so 1 over 3 factorial remains. But this combination, which I'm about to show after the fact, is the determinant A times delta IJK LMN. IJK LMN. And the B terms remain. B, L, I, B, M, J, and B, N, K. B, N, K, and of course here, what we have combined with 1 over 3 factorial is capital B, the determinant of B. So the result is AB. Almost fit. So, to summarize, C equals AB. In other words, the determinant of the product equals the product of determinants. Very great. A very beautiful and, to me at least, visually appealing proof. And what's also nice about it is that it shows that all of the intelligence of permutations and everything else that goes into the definition of the determinant is actually effectively absorbed into these tensor objects. So look, at any point along this argument, did we have to think really about what's going on. We just really slid through the entire argument on the formalism of the tensor notation, which is a very appealing property of the tensor notation and really shows its power, not to mention how short this argument is. Now let me explain this simple relationship that I used in the middle of this. Here's how I arrived at what I used. What we showed early on is that EA multiplying RST. Let me start from the other end. Is that EIJK times AIR AJS AKT equals the determinant A times ERST. ERST on the bottom, of course. ERST. ERST. And let me multiply both sides by ELMN. ELMN here and ELMN here. And of course, these two permutation symbols combine to give a delta system, LMN IJK. And these two delta systems combine to, permutation system combines to give delta ELMN ERST. So let's put that in and realize that this is precisely the relationship that I used above. Delta LMN IJK. Delta, let's see what's surviving. LMN RST. LMN RST. And that's precisely what I used above, even if the letters are a little bit different. Delta IJK RST times pick out the three A's. Right, that's what I did here. And the result is A times the corresponding delta system with properly chosen indices. So that's the identity that I used here. That is just an immediate consequence of one of the earlier identities that we used before. And of course, if now I contract on LMN and RST, so I take RST in terms of LMN, here I will have 3 factorial times A, and here I will have a formula that we now use as the definition of the determinants. So there you go. We've covered determinant, the definition of the determinants, we included a discussion of the delta systems, and we now used all of that, although the discussion of the delta systems was not relevant for this proof. But then you can say we went back to determinants and proved the very important product property of the determinants, which I think is best shown in tensor notations, and this was in tensor notation, and this was one of my several motivations in the beginning of the book for the tensor notation. Okay, next we'll discuss cofactors. Okay, let's talk about cofactors. Cofactors are actually another topic that's best studied from the book, I feel, because it has a lot of technical details and just little small things you have to pay attention to and realize that some of the terms are the same and so forth. So here we'll skip those details, you can call them technical details, and we'll just focus on the big picture of cofactors. And again, I'm assuming that you remember what cofactors are from linear algebra. And I will, in a moment, write down the definition of a cofactor, and we'll just accept it as the definition. It'll be up to you to match it up to what you already think of as cofactor when it comes to matrices. The most important property, there are 2 important properties of the cofactors, so might as well mention them at the beginning. One is that a cofactor of a matrix is almost its inverse. I'll explain in what sense that is. I'll just mention what it is, and it's up to you to work through the details. But equally importantly, it will represent the derivative of the determinant with respect to an entry of a matrix. So you can think of a determinant of a 3 by 3 matrix as a function of 9 variables, where the variables are the entries of the matrix. And as a function of those 9 variables, it's actually somewhat linear in each entry. So the determinant is not too hard to calculate, but that's the point. The determinant can be calculated, the derivative can be different. It can be considered, so the determinant can be considered as a function of 9 variables, the 9 entries of the matrix. It's almost a linear function of each of the matrix, but as a combination of those variables, it's a very complicated function. So it can be differentiated with respect to each one of the entries, those 9 derivatives, or n squared derivatives. And it's very frequently needed in calculus applications. So we will compute the derivative of a determinant with respect to the entries of the matrix. And the cofactor will pretty much be the answer. So let me remind you of this is the definition of the determinant of the matrix A. So now from this definition of the determinant of the matrix A, we will skip the first term, and we will skip one of the terms in the factorial. We'll only use n minus 1 factorial. And the result will be this new system. That's 3 by 3, 2 indices. I, of course, belongs on top. R belongs on the bottom. And the definition is 1 over 2 factorial times delta ijk RST, skipping the first term, A, S, J, A, T, K. So now, by skipping the first 2 terms, you realize, of course, that we now have 2 line indices, I and R, which were previously dummied by this term. So they end up here. So this is a 3 by 3 system. This is a system of order 2. And if you think about it from the tensor point of view, if A is a tensor, then this is a tensor of 1 contravariant and 1 covariant order. And of course, I now just realized that I forgot to mention one very important consequence of the delta system being a tensor. One of the important consequences is of this system, this 2-dimensional system, matrix, is a contravariant covariant tensor. Is a contravariant covariant tensor. Then its determinant is an invariant, which follows immediately from this formula. Just one of the great benefits of tensor calculus. Okay, so with that in mind, this is called the cofactor of this system. And what are its properties? So let me just write down the first property. The first property is that it's almost the inverse. Here's how it works. If we were to multiply AIR by ARJ, if this was truly the inverse, we would get delta IJ. But what we instead get is the determinant. It's the determinant times delta ij. So this isn't quite the inverse of the system. It's the inverse times the determinant of the matrix A. Okay, so nearly the inverse. It's a multiple, straight multiple. That multiple is the determinant of the system. So if we were to take this cofactor and divide it by the determinant A, then it is indeed the inverse of the system. So this is very consistent with Cramer's rule, where we need a division by the determinant of the matrix. Okay, so that's super important property number 1 of the cofactor. Works in all dimensions. And we'll now mention, and maybe even demonstrate, the second important property of the cofactor, which is the fact that it represents the derivative of the determinant with respect to each of its entries. So let's try and now think of this matrix, think of this value as a function of the 9 entries of the matrix. And take the derivative respect to one of these entries. We need two new letters, so we'll use M and N. M and N. And see what we get. Hopefully we'll get capital A of N, M. That's right. N on top, M on the bottom. Because here M is on the bottom and N is on the bottom of the bottom, which we can think of as the top. And we need two new letters because all of the letters I, J, K and R, S, T are dummy indices in this expression, so no longer available. Okay, so if we write down this definition, it will be, well, 1 over 3 factorial comes out. And in fact, the delta system is, of course, a bunch of constants with respect to the entries of the index. And what we have is the derivative with respect to one of the entries applied to this product. A R I, A S J, A T K. The next step is to apply the product rule. 1 over 3 factorial remains unchanged. The delta system, I, J, K, R, S, T, remains unchanged. And here, by the product rule, we will now have 3 terms. One where the derivative is applied to this, one when the derivative is applied to this term, and one when it's applied to this term. So we'll only write down one of them, and then we'll make the claim that all 3 terms are the same. Not too hard to believe, but it'll be up to you to make sure that's the case. That's described in great detail in the book, as is this relationship. It is proved in great detail, unfortunately with a typo, for which I apologize. So, let's see. So what I'm about to write here, let me first work that out, is the derivative of A, R, I with respect to A, M, N. And that's where, we just have to be very careful about what we're looking at. And of course, we're looking at one of the entries of the matrix, 9 entries of the matrix, differentiated with respect to another entry of the matrix. And that, of course, is either 1 if it's the very same entry, or 0 if it's a different entry. We just have to now capture this observation in a nice way. And a nice way to capture this observation is to capture it with 2 Kronecker deltas. Delta Rm, delta N I. That doesn't seem right. No, that's exactly right, actually. Mn, delta I on the bottom, N on top. Right, so of course we could have flipped these, and that would have preserved the meaning of this expression. But we just want the indices to play nice with the rest of the expression. So, delta Rm, delta Ni, delta Ni, A, S, J, A, T, K, plus 2 more similar terms, and it will be up to you to prove that the 2 terms are the same. Okay, now imagine that this full Kronecker delta comes inside the parentheses for each of the 3 terms and interacts with these Kronecker deltas, which renames R into M and I into N. So the result is 1 over 3 factorial delta, well, open paren. The first term is delta N JK, delta MST, ASJ, ATK, plus 2 terms, which work a little bit differently, but actually end up equaling this term, up to you to prove. And because I claim, and it's true, that these three terms are the same, this 3 is cancelled, and actually becomes 1 over 2 factorial, delta n j k m s t a s j a t k. And of course, we're basically looking at the definition of A and M. So that's the very important property of the cofactors. A, M, and on top. Just like I mentioned before. A and M. And remember appropriately that this is the determinant times the inverse. So this completes our discussion of cofactors, but before I turn the camera off, let me find a nice spot and actually show you how it will be used. It will be used for deriving the Gauss-Weil formula. A very beautiful formula for calculating divergences and Laplacians. And one of the key ingredients in deriving that formula would be to calculate the derivative, and let's try writing on the whiteboard, of the determinant of the metric tensor with respect to one of its entries. Now this is a little different, but not fundamentally different, because now we're looking at a system with 2 lower indices. So we can no longer use these nice delta systems. What we'll be forced to use is product of 2 permutation systems with both upper indices, or both lower indices. Upper indices when dealing with this one. So things would just become a little bit larger, but nothing will fundamentally change in the definition. Except, of course, the determinant of the covariant metric tensor is itself not a tensor, because it's the determinant of a system with 2 lower indices, and this nice argument is not available. But what this is, it will be the cofactor of this system, which of course is the determinant of the system times its inverse. So beautiful. The derivative of the determinant of the covariant metric tensor with respect to one of its entries. You might not be able to see why this is relevant now, but we will surely do in the lecture on the Gauss-Weil formula, beautiful formula, is z comes back, the determinant of the covariant metric tensor comes back, times the contravariant metric tensor. That's the consequence of this beautiful relationship and this, the number 2 important relationship of cofactors. So just about our only takeaway that we will use will be this formula, and I'm really looking forward to the lecture on the Gauss-Weil theorem, because it's really one of the most beautiful formulas in tensor calculus. Okay, thank you very much. See you next time.